online tutorial class where physics is brought at your doorposts. Now today we want to study physics again. In our previous class we talked about capillarity, where we define capillarity as the tendency of a liquid to rise or fall in a narrow tube. We equally talked about the forces that are responsible for the capillarity action of the liquid. And what are those forces? We talked about the force of cohesion, the force of adhesion, and also what? Surface tension. Now we equally talked about the applications of capillarity, where we can apply capillarity. We say we can apply it in our lamp wick, the ability of our lamp wick to absorb the liquid paraffin. Also, the movement of water from the roots of the plant to the upper part of its xylem. So these are our previous knowledge concerning capillarity. Now today we want to look at viscosity. Let's say it, viscosity again. Viscosity. Now we go to our specific objectives. By the end of the lesson, students should be able to, number 1, define viscosity. Number 2, explain terminal velocity. Number 3, classify fluids according to their viscous properties. Number 4, explain the effects of temperature on viscosity. And number 5, use the diagram to explain the forces that is acting on a steel ball falling through a viscous liquid. So these are our specific objective. Now, what do we mean by viscosity? Now, viscosity is simply talking about friction in fluids. Remember, in your first term, you've talked about friction, and that is friction that occurs in solid, whereby we say is the force that opposes the motion between two bodies that are in contact as they tend to move over the other. So whenever you're talking about friction, two bodies must be in contact. But today we are looking at friction in fluids, and that is what? Viscosity. And when we talk about fluids, it includes both liquid and the gas. So friction equally occurred in liquid and what? Gas. Now, just as there is friction when one surface of a solid slides over another, so there is friction when one layer of a fluid slides over what? Another. Now, let's define viscosity. Viscosity, we define it as the frictional force between the adjacent layers of the fluid as they move past one another. Let's define it again. We say that viscosity is defined as the frictional force between the adjacent layers of what? Fluid as they move past one another. Now, when we are talking about viscosity, you find out that if you get to liquid, for example, you have a beaker of water and you equally have a beaker that contains engine oil. Now you find out that if you drop a spherical stone inside the two beakers, or you use a ball bearing, you drop it inside the beaker of water and you use stopwatch to time it, you find out that the stone falls very fast and gets to the bottom of the beaker of water than when you drop it inside a beaker that contains glycerin or engine oil. You find out that the stone will move in a slower motion before it gets to the bottom of the beaker. And what are we talking about? We are talking about viscosity. Now that means that engine oil or glycerin is more viscous than what? Water. That is why the stone will drop very fast in water, and if you time it with your stopwatch, it will have a little time, a lesser time than when you drop it inside a beaker that contains glycerin or engine oil. The time will be more than when you drop it inside the beaker that contains what? Water. So that your glycerin or your engine oil is more viscous than water. It contains more friction than what? Water. Now, in liquid, viscosity is due to cohesive force between the liquid what? Molecules. While in gases, it is due to what? Collision between the what? Molecules. Now, what are we talking about? We said that in liquid, that viscosity occurs as a result of what? The force of cohesion between the liquid what? Molecules. Why? Remember, we've talked about this force of cohesion and adhesion. We talk about the force of cohesion as the force that exists between molecules of the same kind, while adhesion is the force between the molecules of different types. Now, we said that viscosity occurs in liquid as a result of what? The force of cohesion that holds the molecules of the liquid together. While in gas, we say it occurs as a result of what? Collision between the molecules. Now, when you talk about collision between the molecules, you find out that molecules of gas, remember when we talk about matter, you have the three states of matter: solid, liquid, and what? Gas. Now, you find out that the gas molecules, that they tend to move faster than that of liquid and what? Solid. So these molecules of gas, as they move, they tend to collide with each other, even with the walls of their container. So that collision bring about the what? Viscosity in gas, the collision between the molecules. Now, it is obvious that some liquid flows smoother than others. This liquid, they have less internal what? Friction, as I've explained. For example, it is observed that it is easier to pour water or kerosene from a container than to pour honey or engine oil. Why? Because honey or engine oil is more viscous than water or what? Kerosene. So I've explained that. Now, let's look at the effects of viscosity. Effects of temperature on viscosity. Effects of temperature on viscosity. What effects does temperature have on viscosity? Now, the viscosity of a liquid is affected by temperature. How? The viscosity of a liquid tends to decrease with increasing temperature. Let's take it again. The viscosity of a liquid tends to do what? Decrease with increasing what? Temperature. As temperature increases, the liquid molecules, they move what? Faster. The amount of time they spend with their neighbors decreases, thus decreasing the average intermolecular forces, and hence what? Viscosity does what? Decreases. Now, what are we talking about here? Now, let's take, for instance, if we consider a palm oil, your red oil. Sometimes you find out that when you buy your red oil, inside the gallon, they will be very, very thick, that you cannot easily pour them out. Now, and when you want to pour them out, what are you going to do? You begin to heat them up, or you put them inside the hot water so that they will begin to do what? Melt. And when you put them inside a hot water, you find out that their viscosity begins to do what? Decrease. They will no longer be as thick as they were before. Now you find out that hot water serves as our what? Increasing what? Temperature. So as you increases the temperature, viscosity does what? Reduces. So you find out that that red oil become less dense, unlike how it was before. Before it was very dense, but while you now put it inside a hot boiling water, the viscosity reduces, decreases, and it becomes less dense. It becomes lighter, to no longer be what? Thick. So you have seen the effect of viscosity on what? Liquid. We said that increasing the temperature, as the temperature increases in a liquid, viscosity does what? Decreases. Viscosity does what? Decreases. Because there is a decrease in the average intermolecular what? Forces. Now, the viscosity of a gas tends to do what? The increase with increasing temperature. The viscosity of a gas tends to do what? Increase with increasing what? Temperature. Unlike that of what? Liquid. Remember, we're talking about friction in fluid, and I told you that when we are talking about fluid, we are including both what? Liquid and the gas. So for gas, we said that the viscosity does what? Increases with increasing what? Temperature. Remember, we said that viscosity in gas is as a result of collision between the gas what? Molecule. Now, this is because the frequency of intermolecular collision does what? Increases, and hence viscosity increases. Now you find out that your gas molecules, as I've said before, these gas molecules, they collide with one another, because in gas molecules, the molecules are very free to move about. Now when you increase the temperature of a gas molecule in a container, or you heat up the gas molecule, you find out that the molecules of these gases, they will gain more what? Speed. They will gain more speed, and as they gain more speed, they do what? They move very fast, and as they move, collision increases. They collide with one another, and even with the walls of their container. So you find out that increasing temperature increases viscosity in gaseous states. Increasing temperature increases what? Viscosity in gaseous states. While decrease in temperature does what? Increases viscosity in what? Liquid states. Now, so let's see. We say that the SI unit of viscosity is what? Viscosity is measured in Pascal seconds. Pascal what? Seconds, or Newton seconds per meter square. Take note, the SI unit of viscosity is Pascal seconds. Pascal, PA, then S is talking about the word seconds. Or you use the other one, Newton seconds per meter square. Newton seconds per meter square. Now, from our explanation, let's look at this table. Viscosities of common fluids at various what? Temperatures. Now we look at some fluids, look at their temperature and their what? Viscosity. Now we are looking at the first fluid, glycerin, just like your engine oil. When the temperature, this one is talking about liquid now. When the temperature of this glycerin is 20, the temperature is low. Viscosity is what? High, 1.42. When you increase the temperature of this glycerin to 100 degrees Celsius, let's look at the viscosity. 1.5 times 10 raised power minus 2, that is 0.015 Pascal seconds. What happened? The viscosity does what? Decreases. The same thing for another liquid, water. When the temperature was very low, 20, you see the viscosity 1.025 times 10 raised power minus 3. That is, the viscosity here is higher. Now, when you increase the temperature to 100, viscosity reduces 2.8 times 10 raised power minus 4. Now, we go over to gaseous state, like your carbon dioxide. Remember, in gases, we said that viscosity increases with increasing temperature. Now, when the carbon dioxide, the temperature is 0. Look at the viscosity, 1.38 times 10 raised to the power minus 5. When you increase the temperature to 100, viscosity increases to 1.85 times 10 raised to the power minus 6. Another gaseous state, in another gas we have air. Now, when the temperature is reduced to nothing, 0, you find out the viscosity of this air, 1.74 times 10 raised to the power minus 5. Now, when the temperature increases to 25 degrees Celsius, you have the viscosity 1.79 times 10 raised to the power 5. So this has proved our explanation, the effect of temperature, what? Viscosity. Now, let's look at viscosity or viscous force give rise to an opposing force that impedes the motion of object through fluids. Now, the opposing force is known as what? Drag. Force of drag, or you call it viscous drag. When a stone or a ball bearing is thrown down a cylinder of a viscous liquid, the downward motion of the body is opposed by the viscosity of the liquid. Now, the more the viscosity of the liquid, that is, the more viscous the liquid is, the more the opposition to the movement of the stone, and hence the slower its motion. That is, a fluid with viscosity produces a large drag force of an object traveling through it. Now, what are we talking about? We are talking about the motion of a sphere in a viscous liquid. Now, this is a sphere, your cylinder, and inside this cylinder you have your viscous liquid, like your engine oil. Now, you drop a stone inside this engine oil, which is your viscous liquid. There are forces that are acting on this. Number one, you have the weight of this stone acting downward. And remember, weight is a force because it's measured in Newton and is equals to mass times acceleration due to gravity. So the stone is falling down through that viscous liquid, which is your engine oil. Now, you have another force which we call the upthrust. The force U is an upthrust, is an upward force, an upthrust against the stone. Now, what do we mean by this upthrust? Now, let's take it this way. According to Archimedes' principle, it states that when a body is partially or totally immersed in a fluid, that the body experiences what? An upthrust, which is equal to the weight of the fluid displaced. So what is this upthrust? For example, if you have a gallon inside a water, now when you fill the gallon with water, you have not put it inside the river, the weight of that gallon in air will be different. The gallon will be lighter than when you immerse it inside a water. When you immerse it inside a water, the weight will be lesser. So assuming you went to the stream to fetch water. After fetching the water, when the water was inside the stream, you want to bring it out. You find out when it was inside the stream, you are bringing it out, the weight will be less than when you have brought it out entirely from that water. You experience the normal weight. So that normal weight is what we call weight in air. Then when it was in water, that is weight in water. So upthrust is weight in air minus weight in what? Water. So that is the upthrust force due to that liquid displaced. So whenever a liquid is being displaced, because when you drop this stone inside this engine oil, this viscous liquid, you have displaced a liquid. So this upthrust force is as a result of the liquid you have displaced. Now we have this one, which is the viscous drag. Is a force that acts opposite to the motion of the stone. So as the motion of the stone is moving downward, this viscous force or viscous drag is moving downward. Is doing what? Is moving downward. So a stone, the motion of a stone in a viscous liquid, it experiences three forces. Number one is the weight of the stone acting downward. Number two is the upthrust due to the liquid displaced. And number three, which is acting upward. And number three is what? Number three is the viscous force or the viscous what? Drag that opposes the motion of the stone, which also moves there upward. Now, that will take us to what we call terminal velocity. Terminal what? Velocity. Now, when an object falls freely through air, it eventually achieves a constant what? Velocity known as terminal velocity. This happens when the drag force equals the weight of the stone. So when do we achieve this terminal velocity? We achieve terminal velocity when a body is falling freely through air, and when the weight of that body, which is a force, is equal to the viscous force or the viscous drag. Remember, the weight of the body is acting downward, while the viscous force or viscous drag is acting upward. So when the body is falling freely through air, and a time comes when the weight of that body, which is acting downward, balances or is equal to the upward force, which is the viscous force or viscous drag, in that case we say we have reached what we call the terminal velocity. That is, you have achieved a constant velocity. You have achieved a constant what? Velocity. So we say a similar phenomenon, we can observe it when a stone fall through a viscous liquid like what? Glycerin. Now, the stone or ball bearing is subjected to three forces. As I've said before, the weight acting downward, the viscous force or the viscous drag represented with V that opposes the motion, and the what? Upthrust U due to the liquid displaced and it's acting upward. Now the viscous drag or force acts opposite to the motion of the stone, that is upward. So I've talked about that before. So from our diagram, as I've said, when this stone is falling freely and as it is moving, a time comes when the weight of this stone will balance the viscous force or the viscous drag, and when such speed is attained, we say we have reached a constant or terminal what? Velocity. We have reached a constant or terminal velocity. Now let's look at the equation of motion of the stone that is falling freely in a viscous liquid. Please take note of this equation. You may be asked to state the equation of the motion of a sphere. It can be a ball bearing, it can be a stone that is falling freely in a viscous liquid, and that is the equation Fr, that is resultant force, equals W, which is the weight, minus V, the viscous drag, minus what? U. Please take note. Resultant force Fr is equals to weight, the weight of the stone, minus the viscous force or viscous drag minus the upthrust. Now we define the terms. Fr means the resultant force, W is the weight of the stone, V is the viscous drag, Yu is upthrust on the stone. Now, as I said before, we find out that the viscous force increases with the speed of the stone. So as the speed of the stone or velocity of the stone increases, the viscous drag that opposes the motion of the stone in that liquid equally does what? Increases. So as the stone falls faster and faster through the liquid, the viscous force opposes the motion also increases. So this viscous force is proportional to the speed, which is the what? Velocity of the motion of the stone. Now it increases until at a maximum speed. When you attempt maximum speed or maximum velocity, the viscous drag and the upthrust balances the downward force of the weight of the stone. So as that increases, as the speed of the stone increases, the viscous force equally does what? Increases. So that will happen until at a point when what? When this viscous drag or viscous force and the upthrust, both of them are acting upward, when they balances the weight of the stone, that is the one that is acting downward. Now at such a point, the stone moves with what? A constant, or what we call terminal velocity. Why? Because its acceleration is now 0. So whenever you reach a terminal or constant velocity, acceleration becomes 0. We talk about acceleration when the body is increasing, when the speed of the body is increasing, that is when the body is moving upward or when it's moving downward. When the body is accelerating or when it's moving upward, you find out that the body is accelerating. If the body is moving downward, the body is decelerating. That is when you talk about acceleration. But once the speed is constant, acceleration becomes what? 0. Acceleration becomes what? 0. Now let's see the diagram, the graph of terminal velocity. Now this is a graph of velocity, that is as the speed of the body is increasing versus time. When you plot the graph of velocity, that is when the speed is increasing as the stone is accelerating inside that viscous liquid, and you are timing it using your stopwatch, you are going to obtain a graph that is of this nature. Now you find out that the speed is increasing with time, meaning that the body is acceleration. What is acceleration? Increase in velocity over time. So here you find out that the body is doing what? Accelerating until at a particular point, look at this point now, whereby the viscous drag and the upthrust force balances the weight of the body or the weight of the stone. The body now reaches what we call a constant maximum speed, which is constant, and that is where we have our terminal velocity. So at this point now, that is where you have the terminal what? Velocity. The speed remains constant. It is no longer accelerating. Now let's take example under this viscosity. A spherical stone of a mass 100 grams is released from the top of a tall building. Several seconds after the stone is dropped, it achieves what? A terminal velocity of 25 meters per second. Remember, velocity or speed, you can call it speed, just that your velocity is a vector quantity while speed is what? Scalar quantity. So that measured in meter per second. Another stone of equal dimension but twice the mass is similarly released from the top of the building. Calculate the terminal velocity reached by this stone. Assume that the drag force due to viscosity of air is proportional to what? Velocity. As I've explained before, that as the velocity of this stone or the speed of the stone is increasing, the viscous force or the viscous drag equally does what? Increases. So you can see it here. You assume that this viscous drag or viscosity is proportional to the velocity of the stone. Now you are given the acceleration due to gravity to be how many? 9.8 meter per second square. That is a constant what? Value. Now look at the question again. You have a spherical stone of mass 100 gram and is released from the top of a tall building. Several seconds after the stone is dropped, it achieved the terminal velocity of 25 meters per second. Now, another stone of equal dimension but twice the mass, so twice the mass of 100 gram now, is released from the top of the building. We want to find the terminal velocity that stone will reach. Now, let's see our solution. Now, the first stone, the weight of the stone. Remember, weight is a force. How do we get the weight of the stone? Weight is a force, is equals to mass times what? Acceleration due to gravity. And remember, they gave us the mass in gram, 100 gram. We're going to convert it to kilogram, because before you measure your force or weight in Newton, mass must be in kilogram. So how do you convert 100 gram to kilogram? 100 divided by 1000, and that will give you 0.1 kilogram times the acceleration due to gravity that was given, which has a constant value of 9.8 meter per second square. Meter per second square. So the weight of this stone will give us 0.98 Newton. Now remember, we said that at terminal velocity, the force acting on the stone, they are being balanced, right? So at terminal velocity, the force acting on the stone will be equal to the weight of the stone. Remember that the viscous force will be equal to the weight of the stone. So at that terminal velocity, W will be equals to what? V. Here V is the viscous force or viscous drag. So our viscous force will also be equal to what? 0.98 Newton. Now remember, we said that viscous force is proportional to velocity. We said that as the speed of the stone increases inside the viscous liquid, that the viscous force or viscous drag equally does what? Increases. So this viscous drag V is proportional to what? Velocity. So when we remove the proportionality sign, we put constant K. So V will give us KV. So K will now be what? V, the viscous drag, all over what? V, which is your velocity. So K will give me what? My viscous drag, which is 0.98. You divide it by the speed of the motion of the stone that was given in the question, which is 25. So when we divide that, we will have our K. Our K, that is 0.0392 Newton meter per second. Or Newton meter per second. That's the value of our K, constant. Now let's go over to the second stone. We go over to the second stone, and that is the one we are looking for its terminal velocity. Now remember, the weight of the second stone is twice that of the first stone, and the weight of the first stone, which is 100 gram, we change it in kilogram to be 0.1 kilogram. So we multiply it by 2, that is twice. Then that is my M times G, which is 9.8. So the weight of the second stone is 1.962 Newton. And remember, at terminal velocity, the viscous force balances the weight, or the viscous drag is equal to the weight. So W is equals to V. Here this V is viscous drag. So my viscous drag here is 1.96 Newton. Now remember that velocity is proportional to what? The viscous drag, right? So here V is proportional to K as we did before. V is equals to KV. K is the constant. Now I will make V the subject. V, which is the velocity, the subject. Velocity becomes K all over the viscous drag. And what is our K? What do we have as our K? Our K, sorry, we now have that V is equals to what? K over what? V. And that will give us what? 1.96 all over our K, 0.039 Newton meter per second. Now in this case, my speed, which is my velocity, becomes what? 58.0 meter per second square. 58.0 meter per second square. Please, there is little omission here. Here my V, when I make this velocity the constant, it will be equals to what? The viscous drag over what? K. So this is supposed to be V all over what? K, whereby my viscous drag is 1.96 divided by our K, the constant we've gotten in the first stone, which is 0.0392, and that will give the speed or the terminal velocity of the second stone to be 58.0 meter per second. Now you are going to evaluate yourself with these questions. Number 1, define and explain viscosity. You define it and you explain what you understand by viscosity. Now you explain terminal velocity. When do we have terminal velocity? Number 3, explain the effect of temperature on viscosity, which we talked about the effect of temperature on liquid and what? Gas. Number 4, you draw a force diagram of a stone falling through a viscous liquid. Please, very important. These questions are being asked in WAEC. You know how to draw it. You know the forces that are acting on it, which is number 1, the weight of the stone acting downward. Number 2 is the upthrust of the stone on the liquid, which is acting upward, U. Then and the viscous force or viscous drag on the liquid, which is also acting upward. Then you use a graph to explain how terminal velocity is being reached. So we have come to the end of today's lesson. Thank you once again.